of this session is from the CHAOSS workshop, as I said. Dr. Ioannis, Malliotakis, are you ready?
Yes, I'm ready. Can you hear me?
All right. Yep, I can hear you.
Good.
So that the next speaker, the Ioannis, will talk about his paper titled "Optimizing Memory Mapped I/O with Huge Pages for Fast Storage." So that the host will play your the video soon.
Hello, my name is Ioannis and today I'm going to be presenting HugeMap, optimizing memory mapped I/O with huge pages for fast storage. This is a joint work along with Anastasios, Papagiannis, Manolis, Marazakis, and Angelos, Bilas, who was also my thesis advisor during the writing of this paper. The current status quo for data-intensive applications is to use read and write system calls along with the user space DRAM cache in order to reduce system call overheads. These user space caches, however, require frequent lookups, even for hits. Thus, the main drawback of this approach is that system calls along with cache lookups cause substantial CPU overheads. An alternative is to use memory mapped I/O, or MMIO for short. With MMIO, we can map a file or a device to the virtual address space of the process. Then, accesses to in-memory data bear no cost, because page lookup is performed via the memory management. On the other hand, accesses to unmapped regions incur page faults, which require processing by the kernel. The kernel also manages page eviction and replacement upon DRAM pressure. Another important facet of MMIO is that it requires no data copies between kernel space and user space. With all that being said, MMIO has an important drawback, and that is that it produces small I/O accesses. This stems from the fact that I/O requests with MMIO use 4 kilobyte page granularity, and thus applications with sequential or large I/O patterns may suffer overheads from I/O merging. Our work seeks to tackle this issue. We wish to use huge pages with MMIO in order to reduce the need of merging for inherently large I/Os, reduce the number of page faults and associated page fault processing overhead, and reduce TLB pressure by reducing TLB entries. All that is well and good. However, the Linux kernel does not support file-backed huge pages by default. So our work, HugeMap, provides this file-backed huge pages. This is a brief outline of what we're going to cover today. Now that we have seen the motivation behind HugeMap, let's take a look at some background info regarding huge pages in Linux. Regarding the support for huge pages in the Linux kernel, on x86-64, 3 page sizes are supported. Firstly, 4 kilobyte regular pages called PTE mappings. 4 kilobytes is the default page size in Linux. Secondly, 2 megabyte huge pages called PMD mappings. It is these huge pages that HugeMap utilizes. Lastly, the somewhat unwieldy 1 gigabyte huge pages called PUD mappings. There are currently 2 kernel mechanisms for huge pages. The first is called transparent huge pages, or THP for short, and the second is called huge TLB pages. Let's take a look at these two mechanisms. THP is a transparent kernel mechanism. With THP, sets of 512 contiguous 4 kilobyte pages can be promoted to 1 2 megabyte huge page, or vice versa, a 2 megabyte huge page can be demoted and thus broken down to 512 contiguous 4 kilobyte pages. Responsible for these promotions and demotions is the kernel daemon thread kHugePage. It is configured via sysfs. On the other hand, hugeTLB is an explicit huge page request mechanism. A kernel boot parameter can be set in order to allocate a huge page pool in kernel space. Then, static huge page requests can be issued to this pool via the special file system hugeTLBFS. The main drawback of hugeTLB pages is that they cannot be swapped out under memory pressure. And, as well, the major problem with both of these mechanisms is that neither of them actually supports file-backed mappings. So, what do we need to do in order to provide file-backed huge pages? Well, first of all, we need to allocate 2 megabyte compound huge pages via the kernel allocpages function. Then, we need to associate our custom huge page fault handler with the virtual memory areas which are created using mmap via the VM operations track, which contains a huge page fault handler function pointer field. Lastly, we need to enable THP, even though we do not use it. The reason for that is that when enabling THP, certain flags are set which are necessary in the kernel page fault path in order for our custom huge page fault handler to be actually called. Let's look into some of the design principles of HugeMap. HugeMap is a kernel module which implements an optimized MMIO path. This figure depicts the Linux I/O stack. HugeMap operates on the mmap layer. It is built as an extension of FastMap, more info on which you can find at the proceedings of HugeMix ADC 2020. HugeMap is designed to operate over either an underlying device or a file system. This can be configured when loading the module via its provided IOCTL interface. Thus, the read or write requests that HugeMap issues use either the kernel bio API when over a block device or the file system operation functions when over a file system. HugeMap utilizes a DRAM page cache. This page cache is organized using different per CPU core structures. These structures include a radix tree with clean and dirty pages, a red-black tree containing only dirty pages used to quickly find dirty pages for write-back, and a free list containing only available clean pages used to quickly find clean pages in order to self page faults or evict pages. We also have a set of kernel threads which asynchronously clean pages via write-back in order to always have available clean pages. These kernel threads begin operation once the amount of dirty pages exceeds 75% of all pages in the page pool. We have also implemented a custom huge page fault handler which is responsible for serving huge page faults, updating the above mentioned structures, and doing all the necessary bookkeeping for the module. In its current state, HugeMap only supports the exclusive use of either 4 kilobyte pages or 2 megabyte huge pages, and it is possible to switch between these configurations at compile time. Now, let's look into the operation of our custom huge page fault handler. So, we have a huge page fault. We need to allocate a clean page from our DRAM page pool in order to serve the page pool. Then we reach our first impasse. We need to check if there is a clean page available in order to serve the page pool, or equivalently, if we've already found the desired page, because we also have page faults for read-only pages that are then attempted to write on. If this is not the case, then we need to evict our least recently used clean pages from our per CPU core free list. We use the least recently used policy for this, and then we clear the associated page table mappings. We then reach our next decision point, and we need to ask ourselves if the page fault was caused by a write operation. And if it was, what we need to do is to update the page young and dirty bits, and we also need to call our custom mkwrite function, which performs the necessary bookkeeping for our per CPU core structures. After all this, we need to create the page table mapping, and then we return VM fault no page in order to indicate to the kernel that our huge page fault handler has taken care of everything and no further operations are necessary. We are going to continue with some results from our evaluation. These are the specifications for our experimental testbed. We used a server with 2 Intel Xeon CPUs with a frequency of 2.4 GHz, each equipped with 32 hyperthreads. We also used an Intel Optane SSD with a capacity of 375 GB. Our server was equipped with 256 GB of DDR4 DRAM and ran CentOS version 7.3 over a modified Linux kernel version 4.14.72. In order to limit result variance between different iterations of our experiments, we disabled swapping and CPU frequency scaling. The first major advantage of huge pages over regular pages is the improvement on execution time. Using huge pages, we can firstly reduce CPU system time due to fewer page faults. This stems from the fact that a 2 megabyte huge page corresponds to 512 4 kilobyte regular pages. Therefore, when using huge pages, we can reduce page faults and the associated page fault processing cost by 512 times. Secondly, using huge pages leaves more CPU cycles available for application processing. This is a direct consequence of the reduced CPU system time which huge pages offer us, thus allowing for greater CPU time percentage to be allotted to applications. This figure demonstrates the execution time breakdown for a write-only microbenchmark over our fast device with 32 threads. The green checkered column represents CPU system time percentage. As we can see, the CPU system time percentage is reduced from 94.37% with regular pages down to 20.39% with huge pages, a significant reduction. Furthermore, on the huge page configuration column, we can notice a greater CPU I/O wait time percentage, meaning that with a faster device, we can enjoy even better performance, while the regular page configuration leaves less such margin for improvement. Next, we are going to examine the impact of huge pages on device throughput. Due to the fact that huge pages produce inherently large I/Os without requiring processing expensive merging, it is easier to achieve peak device throughput using huge pages rather than the regular pages. This becomes evident on the following figure, which demonstrates read and write device throughput for our microbenchmarks, run with 32 threads and several configurations. We can observe that for our read microbenchmark, the only configurations able to reach the peak device throughput of 2.5 gigabytes per second are HugeMap with 2 megabyte huge pages and Vanilla Linux with the mAdvice sequential hint. mAdvice sequential is an access pattern hint which essentially instructs the kernel to perform processing expensive page prefetching. Additionally, we can see that on our right microbenchmark, the HugeMap configured with huge pages achieves greater device throughput both for reads and for writes rather than its regular page counterpart. In conclusion, HugeMap improves Linux memory mapped I/O by reducing processing overhead and increasing throughput. When compared to 4 kilobyte page configurations, HugeMap can reduce CPU system time by up to 4.2 times with 32 threads and increase device throughput by up to 3.5 times for writes with 32 threads. It is important to note, however, and we understand that using exclusively huge pages is a problem for small and random I/O access patterns. Therefore, our future work is concerned with dynamically combining huge and regular pages in order to get the best of both worlds. I would like to thank you for your time. I hope you found this presentation informative and concise. You can contact me at the listed email, and I hope to see you / hear from you at the upcoming Q&A. Thank you.
Hello, John. Can you hear me?
Yes, I can hear you. Can you hear me?
Okay. There's a 1, 2, 3, 4, 5. Actually, 1, 2, 3, 4. Four questions on the CHAOSS channels.
Yes.
I mean, would you please read the questions and answer?
Yes, no problem.
Okay, thank you.
Okay, so we have a couple questions first from Michael. Would it have been possible to add support for fileback huge pages to the existing kernel infrastructure? And are we planning to merge our approach into the kernel? Okay, very good question, first of all. And it's difficult to answer because the existing kernel mechanisms are a bit opaque concerning huge pages, if you understand what I mean. There have been some attempts to use huge pages on some existing file systems. For example, a man named Kirill Sutemov has done some work on adding file-backed huge page support for several file systems, including TM3FS. But at its current stage, the kernel cannot support file-backed huge pages without several changes. So regarding the second part of the question, I believe that our first intention is to bring HugeMap to a dynamic stage where we can use both huge and regular pages, and then we could check the possibility of adding direct kernel support for huge pages instead of what we're doing right now, which is a bit of a bypass. And I will also link you to an interesting LWN article regarding the implementation of huge page support in the ext4 file system. So let me send that real quick and I'll move on to the next question. Okay, so this is the article. Okay, so the text question is, if we also investigated the benefits for traditional hard drives or only for Optane. So our thinking was mostly that when using traditional HDDs, which are slower devices, the processing overhead costs are diminished in front of the major cost, which is the access to the HDD. However, when using faster devices like Optane, the CPU overhead becomes significant because the accesses to the fast device are significantly quicker than accessing a traditional HDD. Therefore, we mostly looked into Optane and fast devices for the benefits of huge pages. Okay, so the next question is whether HugeMap requires application modifications. No, it is transparent to applications. The module is loaded over either a device or a file system, and then the application can just issue a traditional mmap call to the device or the file system and use it regularly. So no application modifications are necessary. And we have another question. What is the difference between HugeMap read and HugeMap write on slide 18? So I'm going to share my screen real quick for this one. I have the presentation set up on a window. Can you see my screen? Is everything okay?
I can see it.
Yes.
Okay, okay. I'm going to slide 18. So the difference between HugeMap reads and HugeMap writes is that these microbenchmarks are read-only microbenchmarks. So we only perform, we map a device and then we perform only reads to it. And the HugeMap write configurations, these are write microbenchmarks. So we map we use mmap on our device, and we issue write requests, which require both a read and a write. So that's why for our write microbenchmark, we see both reads and writes.
But why is the read performance lower for the write use case?
I believe because I would have to say that it is because of a shared throughput, because we are performing both reads to the device in order to handle our page faults, and our write back threads are also writing pages back to the device. So we're performing both reads and writes. If we look at the combined throughput, then we again can reach our peak.
But not for the 4 kilobyte version, right?
No, our huge pages reach the peak device throughput, but while 4 kilobyte pages do not, because they require more cores.
Okay, thanks.
Okay. Let me see if we have something else. Okay. What about PMEM? How does the Optane devices or similar compare against this or change what you've done? Okay, so I'm in the bad position to say that I am not aware of PMEM. I do not know what it is. So if you could perhaps elaborate a little bit, or persistent memory devices. So I do not think that the different device types bear with them many changes to our approach and our design, because our initial motivation is that with a much faster device, no matter the type, the processing overheads associated with fault handling and I/O merging become significant to the performance of applications. Therefore, we sought a way to combat this. Therefore, if no matter the underlying device, we offer some benefits. Our standard benefit. I do not know if this covers your question, because I don't know. I think I'm mostly okay.
John, actually, there's one more question on that parameter
Yes.
channel. If you
On the parameter channel, okay.
Yeah.
Okay, can you explain when you choose the huge pages over the small pages or vice versa? If you mean in our current configuration, then it is just a compilation time per processor macro. However, for our dynamic approach, which we are planning currently, it is a question of access patterns, and yeah, it is mostly a question of access patterns. You see, if we make small and random accesses, then huge pages produce wasteful I/O, because we read 2 megabytes of the device space when we only require much less than that, because our access patterns are not sequential. Therefore, in that case, we would prefer to use regular pages, which are smaller and produce less wasteful I/O. Therefore, there have been also some approaches which we have noted on our paper at the related work section to use such analysis of access patterns in order to configure the behavior of page fault handling. I think that it was DRAM I, which we mentioned on our paper. It did not use huge pages as we do. It only had several custom structures and performed some prefetching based on access pattern history. So some analysis can be done with access pattern history and access size in order to dynamically choose between huge and regular pages. Okay, I see that you're currently typing, so I will wait a little bit.
Yes.
Okay, can we know the access pattern beforehand? Perhaps this is how the mAdvise the mAdvise function works. mAdvise is a function which gives hints to the kernel regarding the access pattern that the application is going to use. So we can have mAdvise sequential or mAdvise random, and thus instruct the kernel whether an access pattern will be sequential or random. It is possible to perhaps implement such a hint mechanism for HugeMap as well, or we could use a dynamic mechanism with some warm-up. So we could begin perhaps, let's say, with huge pages by default, and depending on the access patterns that we record, we could choose to switch over to regular pages. Or another approach is perhaps to use something similar to the transparent huge pages mechanism, so that we initially offer huge pages, and perhaps if we see that the access patterns are small, we can break down our huge pages and turn them into 4 kilobyte pages. So this is an area of research with many questions that it is very much open for discussion.
Okay. Seems that you answered all the questions on both channels.
Yes.
Okay, thank you. Thank you, John, for your presentation.
Thank you for your time. Thank you very much.
All right. Thank you. Thank you all for that. This is the end of all the presentations. Michael, Dr. Michael Kohn, are you there? Can you hear me?
Yes, I'm here.
Okay. Do you want to add short remark, closing remark to the session?
First of all, thank you for integrating our single talk into the Paramo workshop. I think it was a very interesting talk. Thanks again, Ioannis. Hopefully next year we will have a slightly bigger workshop with more talks, but this year it turned out like this. Thanks again, and that's it from my side.
All right, thank you. Thank you everyone for your participation of Paramo workshop as well as the CHAOSS workshop. And I especially thank to that the technical staffs hosting this wonderful Zoom webinar so that we can have this nice workshop together. And to speakers, I would like to make a important announcement. The first one is the final camera ready of your manuscript is due on September 25th. It will be delivered soon, that you may already checked. Since that we are publishing your papers in LNCS form, so that please remember that mark the date on your calendar so that you may not miss that deadline. Also, the second announcement, as you may already check on or that of our core 4 papers, we are planning the special issue on the concurrency and computation journal of Wiley, which is SCIE indexed. The last year's invited papers all reviewed successfully and will be published as a special issue soon, so that we have to prepare the second special issue of our workshop invited papers. The detailed information as well as a guideline for the invited papers will be sent to speaker's email in early September. Okay, any questions about that your publication, 2 publications? Okay, please send me email or leave questions on the Slack board so that we can address in timely manner. Okay, again, thank you so much for your participation and see you. I hope that see you next year again at Paramo. Okay, thank you.
Thank you very much.
Thank you.
Bye.
Bye.
Thank you. Bye-bye.
Bye-bye.